Okay, so today we're going to talk about Newton's method, and this is actually one of my favorite topics or concepts that we talk about in this class because it's just so interesting the way it works. So let me kind of just give you a quick idea of what our goal is. So the goal for this section is literally just to find roots of functions by using Newton's method. So you might think to yourself, wait a minute, haven't I found roots pretty much almost in every class? And the answer is yes. Okay, so just to kind of touch base or talk about the types of roots that we've worked with prior to this class is this. So we know how to solve for quadratic equations in the form of ax squared plus bx plus c equals to 0. So, you know, we at this point, we're experts at finding zeros of quadratics that look of this sort. And then we also can find roots of third and fourth degree equations, which basically we have some formulas that we may use. So by using formulas, but these are extremely complicated. So what's happening here is that we don't have kind of like, so let me actually move this up. So we can find equations of formulas, you know, but these could be pretty complicated. So then what we notice is once we go past quadratics, things become more difficult. In fact, if we have degrees, so let's kind of expand on this. If we have polynomials, a degree of 5 or higher, we have no such formula. We have no such formula to solve for the roots. So then the question is, well, how do I solve for these roots if I don't have a formula? And one of the methods that we could use is known as Newton's method. So one method of finding roots is by Newton's method. So let me kind of show you what's going on visually, and then you will see exactly what the main idea here is, and then we'll kind of put this to use. Okay, so by the way, this kind of stuff, you know, since I love it so much, I think you're pretty much guaranteed to get this on a test. Okay, so make sure you know how to use Newton's method. It's actually pretty simple once you get it, and it's very effective because, like I said, there's polynomial functions out there that good luck trying to find their roots, but Newton's method kind of helps us go in the direction of the roots. Okay, so one method, or sorry, I already wrote that. We'd say take into consideration the following graph. So let's kind of, let me graph something that we'd want to find the root of. So if we have a function where its graph, or the part of the graph, looks something like this. So here's f of x. So my goal is to find this root. That's my goal. So what's going to happen is, and here's where kind of Newton's method is kind of cool the way it works. So what we do is we start off with an initial guess. We say, look, why don't I guess as this being my root? Which clearly, obviously, x sub 1 is not my root, but I'm starting off with a guess. I'm saying, look, I'm going to pick some random x value and call that my root. So then what we notice is, if I take this, we've learned in this class that when I'm at this x value, could I find the equation of the tangent line to this curve at that point? Well, the answer to that is obviously yes, because we've done that so much in this class. So what we know is, look, if we have the equation of this function, and I'm picking this as my initial guess as what the root is, which of course it's not, so now we need to somehow get this to become that. What I'm going to say is, look, let's find the equation of the tangent line to this curve at this x value, which practically, here's what we're doing. We're finding the equation of this line. Okay, and then once you do that, then you say, okay, you know what? Finding x-intercept of tangent lines, or any kind of a line, is very easy, because all I have to do is set y equal to 0 and then solve for x. So then what we're going to do is we're going to say, okay, look, this x-intercept is my second guess at what the root is. Now, what did you notice about x sub 2? X sub 2 actually got closer to r than x sub 1. So what you notice is, if we keep repeating this process, the x-intercept of these lines are going to get closer and closer to r, and then they're eventually going to get so close to r where we're going to know exactly what this root is. So then we kind of repeat this process. We say, okay, look, I found this x-intercept using this red line. Now at this x value, let's find the equation of the tangent line to this curve at this x value. So we do the same thing. We come up here and say, okay, look, at that x value, this is the point that's on the curve. Let's find the equation of the tangent line, and this is kind of what we get. So this is my new line, and notice how the x-intercept of this new line is even closer to that root. So what do you notice? Through this process of constantly finding equations of tangent lines and their x-intercept, we get closer and closer to the root. And that's kind of what Newton's method does. Newton's method says, look, if we start off with just any x or any initial guess, we keep finding equations of tangent lines, and then we should notice that the x-intercept of those tangent lines will get closer and closer to a value. They'll settle down to a value, and that value that they settle down to, that's the root of this polynomial function. So as you could see, if I were to continue this process and say, look, at this x value, let's find the equation of the tangent line to this curve, and it literally looks like I'm pretty much, I'm not exactly, but what you notice is this last line is practically x sub 4 is exactly where r is. So hopefully, you understand how cool this idea is, because all we're using are equations of lines, and these equations of lines are practically getting us closer and closer to our root. So that's Newton's method. This is kind of like one way of doing this, but there are other ways as well, but Newton's method is what we're going to work on to approximate or to find roots of polynomial functions. So let's kind of write out the steps involved in Newton's method. So let's go through this. So here's how Newton's method works in finding r. So the first thing is, this is actually the fun part, you start with an approximation. So you make your guess. So start with an approximation x sub 1. So you just pick some random x value and say, this is what my root is. So one thing you'll notice in your choice of x1, your initial guess, the closer you are to the actual root, the less equations of tangent lines you'd have to find. The further you are, you probably have to go through this process more and more and more, but eventually it should level down to your root. Now, sometimes, of course, there's other equations or guesses of, or initial guesses of x1 where it kind of takes you to the wrong place, or you end up getting nothing. And we'll talk about how sometimes you could tell by your initial, if your initial guess was a good guess or not. Okay, so once you do that, then you could, we're kind of going to go through the steps. If you remember, we made our initial guess, x1, and then what do? We found the equation of the tangent line at x1 to this curve. So what we would say is find the equation of the tangent line to the point x sub 1 comma f of x sub 1, right? This is the point that is on that curve that we talked about, which of course the equation is what? Y minus f of x sub 1 equals to f prime of x sub 1 times x minus x sub 1. And then once we did that, if you remember, what do? We grabbed this line and we found its x-intercept. So the third step was find the x-intercept of the tangent line. And what we'll do is we'll call this x sub 2, which basically, if we go back to my picture here, x sub 2 is this guy. So then what we do is we go ahead and go on to the next process. So the good news here is we could come up with a formula that works. So look at what we get here. So write a formula for x sub 2 in terms of x sub 1. And then we would say, look, remember that x sub 2 comma 0 is on the tangent line, right? Because what is x sub 2? X sub 2 is practically the x-intercept of your tangent line. So if this is an x-intercept, x sub 2 comma 0 is on the tangent line. So here's what the equation of x sub 2 would be. To find x sub 2, we're practically grabbing the equation of this tangent line up here, and we're replacing y with 0 and x with x sub 2. And then once we come up with the formula for x sub 2, we could see how we'd come up with the formula for x sub 3, and so on. So we would get what? 0 minus f of x sub 1 equals to f prime of x sub 1 times x sub 2 minus x sub 1. Okay, so as I said, I took the equation of the tangent line, I replaced y with 0 and x with x sub 2. Okay, so moving on to the next page. So now, that implies that we get x sub 2 equals to x sub 1 minus f of x sub 1 over f prime of x sub 1. So what we just came up with was a formula to find x sub 2. So you don't even need to go through the process anymore of finding the equation of the tangent line, because that's what we did. We pretty much generalized it and said, look, if I want to find x sub 2, I need x sub 1, which we have because that was the initial guess that we came up with. And then I need the y value of my function of x sub 1, which we have that because if we have the function, I could just plug in my initial guess and get the y value, divided by find the derivative of f and plug in x sub 1. So this does the same thing as everything we did basically over here. So the good news is we just came up with a formula. You don't need to find the equation of the tangent line. All you really need to do is just find the formula we came up with by using the tangent line. So this will basically do everything for you. It'll find the equation of the tangent line, but it'll at the same time find the x-intercept of the tangent line. So this is pretty much the formula we want to go with. But then how do I find x sub 3? Well, once we find x sub 2, we repeat the process, the same steps that we talked about. So what we would say is we repeat steps for x sub 2 to get to x sub 3. So it's kind of like we go back now, instead of x sub 1, we do the same thing for x sub 2. And since the good news is we came up with a formula, this would give, which gives, what would that be? How would I find x sub 3? X sub 3 would equal to x sub 2 minus f of x sub 2 over f prime of x sub 2. Okay, so if I do this n times, so now let's kind of generalize this. The nth approximation is, so the nth approximation, if I'm going to do this n times, it'll be what? X sub n plus 1, right? Because the nth approximation, x sub 1 doesn't count as an approximation. That was our initial guess. So the nth approximation would mean we're getting the n sub n plus 1th term. So x sub n plus 1 would be what? F of, or x sub n minus f of x sub n divided by f prime of x sub n. So this is kind of like the process we're following. Okay, that's exactly what we're doing here. Okay, so this is Newton's method. Okay, but you know, I'd rather you didn't just memorize the formula. I'd rather you understood exactly what's going on, because that's so interesting, like the way this works. Okay, so now some comments I want to make here. If the numbers x sub n become closer and closer to r as n becomes large. Okay, so what am I saying? As my iterations, or when I keep going through this process over and over and over, when you get closer and closer to r, which is our root, as n becomes large, and so what's n? N is something that you're looking at as it goes towards infinity. Then we say that the sequence converges to r, and the limit as n goes to infinity of x sub n equals to r. So when I tell you that the sequence or something converges to r, what does that mean? If I take an equation and I repeat the process as much as possible, this will start settling down to the number r. So if I tell you that something converges to r, that means in the long run, it's going to get closer and closer to r, which basically this is what this is saying, right? If I go through this process infinitely many times, these roots are going to approach r. Okay, so before we wrap this up with an example, I want to make another comment as to circumstances that things can go wrong. So we could say that there are some circumstances where the sequence may not converge. Which it could basically, if it doesn't converge, it diverges. So here's what we could say. Consider if I have an example such as this. So look at this, basically this graph. So what's my goal? Let's say my goal is to find this R value. So what's going to happen here? Well, for example, first of all, you could already see what would be a bad initial guess. If I pick this as my initial guess, what would be the problem with this? Then I'd come to this curve and find the slope or the equation of the tangent line, which is horizontal. And what's the problem with this? This has no x-intercept. So right away, if you notice that the slope of your tangent line is 0, chances are you picked a pretty bad initial guess. Okay, so that won't work. What would be the next problem? What if I picked, for example, this as my x sub 1? So let's kind of get rid of this one. What if I picked this as my x sub 1? Then if I found the equation of this tangent line, it would take me here, which so far it looks good. Then if this is x sub 2, what would I do? I'd go to this curve, or I would find the equation of the tangent line to this curve at x sub 2. And what would happen here? If I find the equation of this tangent line here, what do I notice here? X sub 3. Now I'm kind of like out of bounds. Okay, so you should be able to tell if your initial guess is not good one. Because this one, what happens is when I'm out of bounds, I have no curve here to find the equation of a tangent line anymore. So I kind of went away from R. So usually, one comment I'll make is that when our, so we could say that initial guesses may potentially be inappropriate guesses if the slope of the tangent is close to 0. Okay, so that's when you kind of should have a guess as to, you know, have a good idea as to, hey, was my initial guess a good one or a bad one? If you get a slope of a tangent line that's fairly close to 0, chances are it's not, you may not get, um, you may not be able to find the root that you're looking for. Okay, so the steeper the line, usually the better off we are. Okay, so especially, well, if the equation of the tangent line or the slope of the tangent line is exactly 0, that's, you definitely have to start over again. Okay, but even if you get slopes that are close to 0, you just might want to proceed with caution, or maybe you want to pick another initial guess. Okay, because it's not that difficult to take another guess. Okay, so kind of, hopefully you see some examples here, like this was a bad one, and then this one, kind of what happened was the slope of the line wasn't steep enough. That's why it kind of took us to somewhere else. If I picked another initial guess where it was steeper, then it would take us to this root. But in this case, the slope wasn't steep enough. So usually what happens is when we run into problems, it's because the slopes of the tangent lines are not steep enough. Okay, so with that said, we can just always start off by picking another guess. So let's actually look at our example, and then we'll be done. Now remember that to know how to do this, because this will definitely show up on your test. I'm definitely going to make you responsible for this. So starting with x sub 1 equals to 2, find the third approximation to the root of the equation x cubed minus 2x minus 5 equals to 0. So basically, here we go here. So our initial guess is x sub 1, which is 2. So if we want to find a third approximation, I need to get to x sub 4. So we know the process here. So we're trying to approximate the root of this, or we're trying to get close to the root of this. So what would x sub 2 be? We know that it'll be x sub 1. It was plus f of x sub 1 over f prime of x sub 1. Okay, so basically, or and it shouldn't be a plus, it should be a minus here. I'm practically using this formula right here. Okay, so what do we have? X sub 1 becomes 2 minus f of x sub 1, which would be practically this guy plugged in 2. So what I'm going to do is I'm just going to use my calculator to do that. So it will be, let me get rid of this as well. So I'm going to put the function and its derivative here, just so I can use a table to easily figure these out. And then its derivative would be what? 3x squared minus 2. Okay, so if I go to the table, what do I care about? X sub 1 is 2, so if I plug in 2, what do I notice? The original function is -1 and the derivative is 10. So this would be -1 over 10, okay? And so this becomes 2.1, okay? So now to find x sub 3, x sub 3 would be x sub 2 minus f of x sub 2 over f prime of x sub 2. And we said our x sub 2 was 2.1, so this would be what? 2.1 minus f of 2.1 over f prime of 2.1. And if I do that, I get what? So if I plug in 2.1, I get 0.061 and 11.23 for the derivative. So this would be 2.1 minus 0.061 over 11.23. So what does that become? If I just use my calculator here, it'll be 2.1 minus 0.061 divided by 11.23. And that will be about let's call it 0. Let's go over to as many decimal places, 0, 9, 4, 5, 6, 8. Okay, so then finally, x sub 4 would be x sub 3 minus f of x sub 3 over f prime of x sub 3 equals to 2.094568 minus f of 2.094568 divided by f prime of 2.094568. So if I do that, if I go to my table and I put in 2.094568, I get 1.8 times 10 to the negative 4. So this would be 2.094568 minus 0.00018 over 11.162. So if I use my calculator, I get 2.094568 minus 0.00018 divided by 11.162. And that gives me about 2.09455. And so what do you notice here? I'm getting closer to what number? It looks like 2.09. So if I want to be more certain, I would go through more steps. But since this direction said find the three iterations, I could stop here. But we could see that our root is very, very close to 2.09. Okay. Now for the problems that you work in class, it might say keep going until you have these matching up to the first 6 decimal places. So I'll keep going until the 6 decimal numbers match up. So right now I match up to what? 4 decimal places, right? 1, 2, 3, 4, 1, 2, 3, 4. So I would keep going until 6 of them match up. So then what happens is you get so close, it's converging to a number, okay? So this is pretty much Newton's method. If you have any questions, feel free to ask. Like I said, the idea is simple, although the computations might be pretty complicated, but we're using our calculators, so you might get messy numbers, which that's fine, okay? But you would never be able to find this root by hand. So it's kind of like Newton's method gives us this advantage of solving or finding roots that we didn't imagine we could without a graphing calculator, okay? So that's basically it. That wraps up this section. So as always, if you have any questions, feel free to ask me.